Tokyo University of Agriculture and Technology is the only national university in Japan composed of a Faculty of Agriculture and a Faculty of Engineering. Through education and research in agriculture, engineering, and their common domains, our founding philosophy is mission-oriented research and education giving synergy in endeavors toward a sustainable Earth. The Faculty of Agriculture is located in Fuchu, in the western part of Tokyo. The expansive, nature-rich campus offers advanced equipment and facilities for research. And the Field Science Center offers wide-ranging agricultural fields. The main building was constructed in 1934 and is now used as the main hall and auditorium. In 2000 was designated as a registered tangible cultural property of Japan. The Faculty of Agriculture consists mainly of 4 fields: agrosciences, ecosciences, biosciences, and animal sciences. These pursue harmony with communities and the natural environment in their research. The Faculty of Engineering is in Koganei, also in western Tokyo. The distinctive campus is lined with ginkgo trees and features sophisticated urban buildings befitting an engineering school. The Ellipse, built for the university's 140th anniversary in 2011, was built with the latest technologies for energy saving and renewable energy use. The Faculty of Engineering covers environment, life, information, material, energy, nanotechnology, and numerous other engineering-related fields of science and technology. It stands at the forefront of technological research with a spirit of inquiry into natural science and a creative approach toward manufacturing. With its focus on agriculture and engineering, the Foundation of Industry, TUAT seeks to enhance learning and research in the common domains of those 2 fields and is constantly involved in practical research. It also has a strong commitment to international exchange with Western and Asian countries, and it is a leader in Japan in joint research with corporations, passing the results of its agricultural and engineering research to industry in the form of technological transfer.
My major is animal ecology, and I focus on amphibians. I have worked on endangered frog species on Amami Island in southern Japan. My favorite frog species, autumn frogs, inhabit there. They possess an unusual 5th finger on their forehands and use them as a weapon in male-male combat. I have been fascinated by their unique ecology and behavior, and now regard them as the subject of my life's work. Currently, my interests are more in the life history of frogs. Frogs have 2 completely different life stages, each in aquatic and terrestrial ecosystems. The aquatic environment affects tadpoles, and the terrestrial environment affects juvenile to adult frogs. The combinations of the conditions in the 2 environments will determine the fate of the frogs. My current focus is to learn about this fate of frogs in various environments. I truly love animals and ecosystems. I have wanted to know about their way of life, what they do, and why they do so. Everyone asks me, then why frogs? But even I myself don't know the answer. Somehow, I fell in love with frogs, maybe because they were always nearby. I want to show how amazing frogs, animals, and nature can be. Fascination for nature is the most important thing for achieving a better world in terms of nature conservation.
Our research group focuses on exploring key technologies for future wireless and mobile communication networks, such as next-generation cellular systems, optical wireless systems, and vehicular ad hoc networks. More specifically, we develop new signal processing and coding techniques in collaboration with researchers all over the world. Recently, we have been working on a large-scale antenna system. In this system, more than 100 antennas are used as the base stations of wireless networks. This technique allows us to significantly increase the data rate. In particular, we propose a new modulation technique that helps to reduce system costs and energy consumption in this large-scale antenna system. When I was a student, I wondered if I could change the world with my own simple research ideas. After graduating, I worked in industry for 9 years and then joined academia. This is how I realized that close collaboration between industry and academia is important for innovative research. My hope is that our research will help everyone enjoy seamless multimedia communication in a real sense.
I have demonstrated that cell polarity plays a critical role in high protein synthesis in lactating mammary gland cells. In addition, my research results show that their dysfunction is related to incidence of human breast cancer and bovine mastitis. On the other hand, mother's milk is thought to contain not only nutrients for body growth in children, but also factors that develop children's healthy biological function. I focus on brain development and hypothesize that the differences in microbiota by changing milk component would have an impact on brain development during lactation. Now, I am analyzing milk components, microbiota differences, and brain function in several knockout mice through meta-analysis. In the future, I would like to propose the presence of a multi-organ network that included mammary gland, microbiota, and brain function. When I was an undergraduate student in this university, I was greatly impressed by the fact that an idea and a pipette was all it took for a researcher to discover various biological phenomena. In humans and other animals, I want to clarify the mechanism by which a mother produces lots of milk and her children grow up healthy.
I work as a Tenure-track associate professor in the Department of Mechanical Systems Engineering. In my research, I develop computer simulation techniques for investigating microstructure evolutions during crystal growth and phase transformations in steels and aluminum alloys through extensive collaborative research with other universities and companies. In particular, we have performed the world's largest scale phase field simulation of precrystalline grain growth using the Tsubame 2.5 GPU supercomputer at the Tokyo Institute of Technology. Through this research, we are trying to reveal the mechanism of grain growth and contribute to development of new materials. I had a great interest in the science of steel when I was an undergraduate student because one of my ancestors was a swordsmith. I want to develop a versatile materials simulator that will contribute to new material development across many industries.
Food intake regulates energy balance, and its dysregulation can lead to metabolic disorders such as obesity and diabetes. During feeding, gut microbiota affect host nutrient acquisition and energy control, and can influence the development of obesity and diabetes. So far, we have reported that dietary fiber and the gut microbial metabolites short-chain fatty acids exert multiple beneficial effects on host energy metabolism, not only by probing the intestinal environment, but also by directly affecting various host peripheral tissues via short-chain fatty acid receptor GPR41 and GPR43. I have long been interested in life science. I decided to pursue it more deeply, and when I realized it, I had become a researcher. We believe that these results will provide valuable insights into therapeutic targets for treating metabolic disorders, such as obesity and diabetes, and the use of probiotics to control gut microbiota.
We study liquid or gels confined in an extremely small space. In particular, the systems we study are within 1/100th of 1 millimeter, the size of a live cell. Such small liquids and gels, called microdroplets and microgels, show quite different behaviors from those in beakers. To analyze the fluidity and elasticity of the microdroplets and microgels, we use a confocal laser scanning microscope and micropipette. Based on our analysis, we try to establish principles to describe life as living matter and build the fundamental technologies of new materials for our daily life. I really like living things, but not biology. When I was an undergraduate majoring in physics, I learned about biophysics and the fun of studying cells from the perspective of physics. I want to fill in the gap between materials and living things and find common principles between them. I will utilize those rules to create useful materials.
The Tenure-track system is an employment and promotion system for young researchers. The Tenure-track system has three fundamental conditions. 1. Posts are open to international applicants. 2. Faculty members work in an independent laboratory environment. And 3. Screening to become a tenured faculty member is conducted through a fair and transparent evaluation. In Japan, a 5-year contract is common for the tenure-track system. TUAT is a pioneer of the tenure-track system in Japan. In TUAT, the tenure-track system is applied to all young associate professors in the Institute of Engineering and to all assistant professors in the Institute of Agriculture, respectively. Distinctive features of the tenure-track system in TUAT are as follows. 1. TUAT adopts the tenure-track system across the university. And 2. From the very beginning of the system, the same number of tenure posts and tenure-track posts is offered, so that the screening to become a tenured faculty member is solely based on the individual researcher's academic achievements. In the screening and evaluation processes for tenure-track faculty members, TUAT includes multiple external committee members to ensure fair and transparent screening and examination. Tenure-track faculty members receive preferential treatment that includes startup budgets, independent research space, assignment of a faculty mentor, educational opportunities, and reduction of administrative and educational task loads. Tenure-track faculty members can promote their own research as principal investigators during their 5-year contract term. Here, we will introduce some of the tenured faculty members who will lead TUAT into the future.
I have studied animal science, especially the field of animal nutrition. as an associate professor at TUAT. My research focuses on dairy cows and chickens. I got tenure 7 years ago, and now I am studying molecular nutrition. This refers to the study of interaction between nutrition, gene regulation, and animal performance. An example of my study is improvement of meat production by increasing muscle cell numbers in newly hatched chicks. My aim is the improvement of animal production and health through this study. I received a prize from Japanese Animal Science Society from the result of my previous research. I was interested in the study of animal science, so I chose a university with such a department. Then I became interested in the nutritional field, and my research continues. I want to contribute to animal production in Japan.
In our laboratory, we have developed basic technologies for energy saving by reducing energy loss owing to turbulent friction drag on high-speed transportation systems such as airplanes and high-speed trains, which are indispensable tools for building a safe, secure, and comfortable society. Specifically, the world's largest superparallel numerical simulations and laboratory experiments using high-speed cameras and laser sheets are being performed to evaluate our unique biomimetic control technologies. First, we have developed a unique three-dimensional livret by further developing shark skins. We have confirmed a world-leading drug reduction effect of about 12%. This offers a wide range of applications, because the control effect can be obtained simply by pasting livret films onto the surfaces of machines. Second, we demonstrated the drug reduction effect of a micro-vibration traveling wave surface simulating dolphin skin for the first time in the world. Furthermore, we have been developing a new ship bottom paint with drug reduction polymer that simulates secretion of fish, such as catfish, and a fluid pulsating control and periodically converging diverging pipe by applying the principle of blood flow pulsation. Our unique biomimetic control techniques are feasible solutions for the near future and could contribute to significant progress in turbulence engineering. The motivation is to more thoroughly understand fluid dynamics, which is the hardest to understand among the subjects I studied at the university. Now we are promoting collaborative research with companies on our unique biomimetic control techniques in order to contribute to global energy saving.